This is Mark Bailey. We ended the last class before exam 3, not getting a chance to work through this problem. So for the sake of those who weren't quite comfortable with calculating the pH of a weak base, I wanted to go through this problem carefully so that you guys could make sure you're comfortable with how to do that. So to start with, this problem is asking us about dimethylamine. And there's two ways that we really need to think about this problem, about whether this is a base or not. I heard a lot of people in class say, well, I gave you guys the Kb, so that means it's a base. This does not tell us this is a base. A lot of times you'll get the Ka and it'll be a base, so you'll have to find what the Kb is. So this just tells us if we have the base form of the conjugate acid base, then we know we can find the other one. So the conjugate is always going to be related, so we could find Ka if we want, but that is not going to be dealing with the base, it's only going to be dealing with an acid. So what we need to do is go back and look at our structure. We could go ahead and draw that out if we wanted to as a Lewis structure. There's 2 methyl groups, so there's 3 total bonds, which means it has to have a lone pair because there's no charge. And that lone pair on the nitrogen tells us it's a weak base. Strong bases are always going to be ones that have an OH- that's formed when it goes into water. So sodium hydroxide is a great example that will form 1 hydroxide and 1 sodium ion in water. Calcium hydroxide will form 2 and 1 calcium in solution. So anything that forms an OH- is going to be a strong base. If it has a nitrogen with a lone pair, or you guys have seen carboxylates, anytime there's a O- that you know would be more stable if it accepted a proton, then this is a weak base as well. So these are typical weak bases. Carboxylic acid is missing the proton, and any nitrogen with a lone pair. Okay, so now we have a weak base, and we're putting that into water. It's always we're going to do with a weak base because Kb says, how does that compound react with water? So we need to find what the pH is of a certain solution. This is the initial concentration. So first we write out the equation, and remember those equations for Kb are always going to be describing taking a base, putting it in water, and then what does it look like once it grabs a proton from water? So that lone pair is going to grab one of those 2 protons. So now that nitrogen has 4 bonds, meaning it has a positive charge, and then water is left as OH-, because when you steal a proton from water, that means we're leaving the bonding electrons behind. Those electrons now will move to oxygen. And so after that's done, you're going to have the O with the lone pairs it had originally, and that bonding pair is now a lone pair, which gives oxygen a negative charge. And that nitrogen now will have 4 bonds and no lone pairs, meaning that nitrogen has a positive charge when that H is part of it now. Okay, so we've written out Kb, and then if you haven't done this already, go ahead and write now what your Kb expression is going to be. So remember that's Kb equals something. Pause for a minute, make sure you can write out your Kb expression. And then think about what the 5.9 times 10 to the negative fourth means about which is going to be more present at equilibrium. So once you've gone ahead and done that, I imagine you would get something similar to this. The concentration of dimethyl ammonium, so we're calling them dimethyl because there's 2 CH3 groups. Ammonium means it's a positively charged nitrogen, right? So dimethyl ammonium times the concentration of hydroxide, all divided by the concentration of dimethylamine. Amine is a nitrogen with a lone pair without positive charge. Alright, so then this value is 5.90 times 10 to the negative fourth, which is the same thing as 1 over 5.90 times 10 to the fourth, meaning we have about 60,000 times more reactants than we do products. So go ahead and draw a Gibbs free energy diagram for this if you would like. If I was to draw it, I would draw all the base form on the left, all the conjugate acid. Right, the conjugate acid is the form that has a proton it can give up. that's on the right. And this one, 10 to the negative fourth, favors reactants heavily, which is our basic form of that conjugate acid base. Okay, so now we talked about K, we've looked at Kb, we've written that out, and now our next step is, well, what are all the concentrations? So I imagine you guys very easily could determine what the initial concentration is. Right, so our initial concentration of our reactant, 1.50 molar, and we're ignoring water for this, we're not focusing on it because it's not a large part of what's going on. So we're going to ignore that because it's not changing. So we have 1.50 molar. Dimethylamine, we don't have any starting there, and we have a little bit of OH minus from the autoionization of water, but we're essentially going to stay here. Then, if we go back and look at that Gibbs free energy diagram, where are we compared to K? So if I redraw that, we're at this. If we look at what Q would be for this reaction, we have all reactants, all the base form, and none of the acid form. So that means that our Q is equal to 0. And that means we're on the far left. So in order to get to equilibrium, we're going to take reactants and make products. So we're going to use up our reactants and we're going to make products. And it's a 1 to 1 to 1 stoichiometric ratio, so that is just x. For all of them, there's no 2x or 4x or anything like that. So go ahead and complete this table, and then think about how we're going to solve. So pause it for a minute and try to solve as much as you can, and then when you're done, come back and we'll walk through it. So that minus x and plus x, we really need to make sure that we're using Q versus K to determine that. And then at equilibrium, we have 1.50 minus x, x, and x for our concentrations, because every one dimethylamine splits up, or becomes one ammonium, dimethylammonium, and one hydroxide ion. So now what do we do? We have Kb, we have this number, we have all our concentrations in the form of with an x. The question is, because this number is relatively small, can we say that the concentration at equilibrium is about equal to the initial concentration before? I think because K is relatively small, it's less than 1, 10 to the negative fourth, we're going to try making the assumption that's stated here. And we're going to use that to simplify our lives in order not to have to do the quadratic equation. So we're going to say that that's equal to x squared divided by 1.5 molar, because that's what came out of our ice table, if we make that assumption. And remember, that assumption is because Kb is small, that x is going to be the change in initial concentration is relatively insignificant compared to how much we started out with. So it's not that x is insignificant, but the big point is that x is insignificant compared to our initial concentration. Okay, so if we go ahead and do that, then if you haven't already, pause and find x. So to find x, we multiply Kb by 1.50 and take the square root, and I found x was 2.97 times 10 to the negative second molar. The big question that you always have to ask yourself, and it becomes even more important when we're doing this for bases, is what is x? So I want you to pause and try to name off as many different things that x is as possible, and be as specific as you can. So we go back to our ice table. What we can look at and say is that x is the decrease in concentration of the initial reactant, that base. X is the increase in concentration of dimethylammonium and the increase in concentration of hydroxide. But because we start at 0, that is also the concentration of hydroxide at equilibrium. It is the concentration of ammonium, dimethylammonium at equilibrium. And so if we use that, now which one of those is going to help us answer the question about what is pH? It's going to be that one that was in the bottom right corner of our ice table, the concentration of OH minus at equilibrium. So before we go any further, I hope that you all thought back and said, well, is the assumption valid? Could we actually say that x, the change in initial concentration, is so small that we can essentially say it's negligible and we have the same equilibrium concentration as we did if we did consider the minus x? So go ahead and check that assumption. If you haven't done that, remember that's a requirement for any time we're doing all this. So when I check the assumption, I compared x, which is our value here, compare that to 1.50 by saying, well, what percentage of 1.50 is our x? If we multiply by 100, we get a percentage, and I get 1.98%. And so, yes, the assumption is valid because that ionization is less than 5%. Okay, so now we're going to go ahead and say, well, I know that x is the concentration of OH minus, and that's the one that we're most focused on, and I can use that to find pH. So go ahead and pause if you haven't already solved for pH, and work through to find pH. And there's two different ways to do this. Both of them are completely fine. So the first way that I solved for pH was, based on Kw, we know that the concentration of H plus ions times the concentration of hydroxide ions is a standard value at room temperature. And we know that's 1 times 10 to the negative 14th. So if I know the concentration of H plus ions, or OH minus in this case, I can find the concentration of H plus. So if we rearrange that equation to solve for the concentration of H plus ions, which will help us find pH, we can just divide Kw, 1 times 10 to the negative 14th, by the concentration of hydroxide. And that will give us concentration of H plus ions. Now we only need to take the negative log of that number, and we find the pH of 12.473. And remember, we had 3 sig figs in our concentration, so that means we have 1, 2, 3 past the decimal. What's the other way we could do this? I imagine that some people found the pOH from concentration of OH minus, and then you know that 14 minus pOH equals pH. Or the other way to say that is pH plus pOH equals 14. So if we go about it that way, we can find that the pOH would be, I didn't do this calculation. You guys can figure it out. You can walk through it. But in the end, we would end up with getting the same pH. Alright, so the last thing I wanted to do is to tie this all back together to Q and K and Le Chatelier's principle. And Le Chatelier's principle is just a really fancy way of saying K is going to be K no matter what. So if we take a look at this second question here, go ahead and take a second to read it. It's on your worksheet as well. We're saying what would happen if we let this go to equilibrium. We got that pH of 12.473, and then we added some dimethyl ammonium chloride to the equilibrium solution. What would happen to the pH? What would happen to the reaction overall? So go ahead and pause and try to figure that out. And I suggest writing out a chemical reaction to help you with that. So if I go ahead and do that, if I write out a chemical equation that would start off with, I'm going to say, well, what is this thing? Dimethyl ammonium chloride. And ammonium should give us a hint that this is probably going to be the acid form. So we know that dimethyl ammonium is this guy, and then it's chloride, which is that guy. So all this really is a salt that when it goes into water will dissolve into dimethyl ammonium and chloride. And now I hope you're thinking, Cl minus, we know that that kind of sits around and doesn't do anything with pH. So this is going to be a spectator ion. Meanwhile, we just saw that if we have dimethylamine and we put that in water, the conjugate acid of that is dimethyl ammonium. And this, by definition then, is a weak acid. All weak bases will generate a weak acid. So, what's going to happen to the pH when we add a weak acid to the solution? Go ahead and make up your mind. So when we add any acid at all, pH is going to go down. Could we calculate how much the pH goes down? Well, before we do that, let's answer the next couple questions here. Would Kb change? Think through this answer, and then let's talk about it. So basically what we're asking is, if we have our Gibbs free energy diagram, we have the base on the left, acid on the right, we have our minimum somewhere over here, that point there is Kb. Is that going to change if we have a different concentration? If we added some of our product in this case? I hope what you're saying is K isn't changing. Then the question is, what did change? We added a product to a reaction that was at equilibrium. So we had Q equals K when we calculated the pH. But then we added some of the acid. So what's going to happen to Q then? So our Kb is not going to change by changing the concentrations, because basically what we're doing is we're saying we were at equilibrium, now we're not, so Q doesn't equal K. So what has to happen in order for Q to come back to K? So go ahead, I guess I already said this. What's going to have to happen in order for this reaction to go back to equilibrium? Will Q change to get back to equilibrium, or what's going to happen? If we go back to this diagram here, what we did was we were at the blue X, and we added some product. That means that we moved this direction. So now in order for this reaction to regain equilibrium, this is all the Chatelier's principle says, is that Q is always going to strive to get back to K. So that means we're going to take some of the acid and convert that back to the base until we have the appropriate relationship described by Kb, because Kb didn't change. I hope that was useful. And in order to study for the exam, try doing some more of these kind of questions on smart work. Take care, guys.